All right. Hi, everybody. Welcome back to office hours. So can someone just say in the chat box if they hear me okay, just to make sure the sound's working? Awesome. And today we're just going to finish the chapter 6 reactions. So we only have 3 more to cover besides these main 6. And we might be able to touch some chapter 7 material, but the goal really today is to solidify all alkene reactions, be able to interconvert between multiple different things, and we should basically at the end of today's video, we should know all of the alkene, reagents, different types of modifications that we can do with those reagents. And it's going to be a gateway into chapter 7 when we start talking about synthesis. Okay, so just make sure you guys know all of chapter 6 by the end of today's video. Okay, let's just kind of jump in, so enough of me talking, and I'm going to do these pretty quickly now because I'm assuming you guys know this. So the first reaction A is the hydrohalogenation reaction. So my click mechanistic arrows are going to be my nucleophilic pi bond attacking that electron deficient hydrogen, and then the electron density between the hydrogen and the bromine is going to be retained onto that bromide. So then we have this regioselective choice. Am I going to put the hydrogen on this part of this carbon-carbon double bond, or am I going to put it on this part of this carbon-carbon double bond? And Markovnikov's rule says to put it on the less substituted side, so that the more substituted side forms that carbocation intermediate. So we're expecting a structure that looks like this, with the hydrogen going there. Okay, you don't have to draw the hydrogen, but again, so then the result was free bromide. Okay, so then free bromide is just going to come back, attack that electron deficiency, and now you have a new chiral center. So remember, those carbocations are unhybridized p orbitals. They have those front and back faces of those lobes. So it could either be the wedge bromide, coming from the top, which forces that methyl group on a dash, or it could be the dash bromide coming from below, forcing that methyl group on a wedge. Okay, and that's it. Okay, no rearrangements here because we were at the most stable position already. That was the tertiary benzylic position, so there were no rearrangements possible there. All right, so again, when we see a series of multiple reagents without distinct steps, so notice how in E we have 1 period, 2 period, that means that these aren't mixed together, they're isolated steps. But you can see in B, when we're talking about acid catalyzed hydration or acid catalyzed ether synthesis, we have this series, multiple reagents together, so we assume that these react first, okay? So the result of that, I'll just draw maybe in red below, is just the protonated alcohol, okay? So what happens is the same series of kind of mechanistic steps, that nucleophilic pi bond grabs this proton, that oxygen retains that electron density. We're left with this, secondary carbocation, which would be right here, okay? We can definitely shift the hydrogen, to the right so that we get a tertiary carbocation. So I hope you guys see that first rearrangement. And so now we're left with a tertiary carbocation, but we can make it a little bit better by making a tertiary benzylic carbocation, so we can do one more consecutive shift. Okay, so I'm moving an alkyl group over, and then that would result in this tertiary benzylic carbocation. So each time we go from secondary to tertiary benzylic. So you can see with each consecutive shift, we're getting more and more stable. So then we can realize that just plain ethanol is hanging out in solution. That ethanol can attack that deficiency, and you're going to form an ether at that tertiary benzylic position. So I'm just going to go right to the products. Or could have been this one. Okay, so I hope you guys got those two. So remember, we can do consecutive shifts, in these hydride alkyl shifts. That each consecutive step is going to lead to a more and more stable carbocation or a more and more stable intermediate. Okay, so C was the one, C, D, E, and F were the 4 reactions I think we did on Monday. Was it Monday? Yeah, Monday. So these are the concerted mechanisms. So, we can draw out bromine again. And remember, these were multiple steps in one. So, we have this nucleophilic pi bond grabbing that bromine, and then that bond breaks because we can't exceed the octet. But in doing so, we developed partial positive character because remember, these electrons are being pulled away. Okay, this pi bond, these electrons are being pulled away to form a bond to bromine, so that leaves this carbon electron deficient. So that would make sense why, a source of lone pairs on this bromide would come back to fix that deficiency, forming this bridge. So I think it's worth noting what that bridge intermediate looks like. You might be asked to identify, what this halonium bridge looks like. And we can see, maybe we have the wedge diversion. okay? And we could also likewise have, the dash version, okay? So this is one, I'll say maybe racemic, so you guys can, actually racemic is a bad phrase to use here because there's another chiral center, so let's just use, plus other. That'd be better, plus other, so you guys understand what I'm talking about. And then, because this is, let's say in this specific intermediate, the bromide bridge is on a wedge, that's sterically hindered now. So the next bromine, the next bromide anion generated from that first step can only attack from the back face, and more specifically at the more substituted side for reasons we talked about. This is a more stable, resonance structure. If I show, that electron, bridge breaking right there, you have a tertiary carbocation there, versus if I were to break that bridge here, it would form a primary carbocation. So that makes sense why this nucleophile prefers that better electrophile right here. Okay, so in doing so, it has to come in from the dash and it breaks over to the right. So, your two structures, I'll go to these products. Hopefully you guys got these, were, okay, and these are my two products, okay, from that. Notice that this chiral center stayed the exact same because we didn't do any chemistry there, and this bromide has no stereochemistry here because the fact that it's not a hybridized center. Part C, if there is dashes and wedges already present, before the reaction GB, okay, so yeah, David, I just said that. Essentially, if you see a chiral center already, like in C, and there is no chemistry there, we're not touching that chiral center at all, we're just dealing with this pi bond, ignore it and leave it the exact same. So the reason why I didn't say racemic here was because they would be diastereomers, because you see it's only partial inversion of these centers right here. So saying racemic wouldn't be the right term there because, it's not just completely enantiomers, they're two diastereomers. Good question, David. All right, so D. So D again is, something similar with this halogen, diatomic halogen, but instead of, the inert solvent, which is, DCM, dichloromethane, we're gonna have water. So some solvent that actually reacts. Okay, so I'm gonna do D a little bit lower because I guess I'm running out of room. So over here, basically I'm gonna draw that same reagent. We have this, chlorine molecule over here, and I lost my red pen, here it is. So, we have this kind of mechanism going on. So let me just draw that intermediate, or one of those intermediates. Okay, so that's one of my bridges right there. And then that free, so not chloride isn't going to attack backwards. We rationalized why water is now going to attack the back phase. And the reason that was is because, chlorine is a lot more electronegative than oxygen. So it makes sense that chlorine wants to retain its electrons more so than oxygen. So oxygen is more likely to participate in bond formation than chlorine would. Okay, so that's why water now would attack this, more substituted position, okay? And then it would break that on the other side, okay? So if you're thinking about your two structures or your halohydrin, you would expect a wedged chlorine, and you would expect a dashed water or dashed alcohol coming in, and it was that wedged methyl at that position as well. So it looks like there is no chiral center here, so I don't actually have to draw that. So this actually turns out, notice how, see, there's two methyl groups, so you don't have to consider the stereochemistry here because it's achiral. So all you really needed to do would be this. Okay, and then, you could draw, the other one with just a wedge. Okay, same thing, right there. Okay, and you guys see why this became achiral, because look, we already had two methyl groups in the beginning starting material. So then when we added that water to the more substituted position, we still had two methyl groups. So that's why it's an achiral center there. Okay, that should be enough for that one. Okay, so for E, these were the funky ones like hydrohalogenation and oxymercuration. So in E, that's oxymercuration. So we have this, mercuric acetate molecule, this inert solvent THF, and water, and then 2 is some sort of reduction step. Okay, but the mechanism is pretty short. Again, it's another concerted mechanism. So let me just draw that out over here. Hg, OAC, OAC, and it's concerted in the sense that, pi bond grabs that hydrogen, has that break off, and then it comes back. So you form this cyclic bridge. I'm going to draw this below. So the cyclic bridge is sometimes asked, Okay, so you could say, maybe we have Hg, OAC positive, and then, you could have the dashed one as well. So this one I can say plus enantiomer. Okay, and then, water is going to be that nucleophile that attacks on the more substituted side. Okay, so water is going to want to attack, this, I guess it looks like this is a secondary carbon and this is a tertiary carbon, so it wants to attack there and break that bridge. So remember, if it does so there, we would expect an alcohol on the more substituted position. Okay, so we would get and we would also get this one. And these are the products of step 1. Okay, those are the products of step 1. And remember, we don't know the mechanistic steps for step 2, but we just know it's a reduction step. So reduction means giving it electrons, or essentially it's a source of, see all these hydrogens right here? So this is an orgo-2 thing, but maybe this helps you. All these hydrogens basically means that I can just replace this entire group with a hydrogen. Okay, so this entire thing is going to go away, that entire thing is going to go away. So remember, the resultant structures of that should be, an alcohol on the more substituted side. So that would be and then those. Okay, so those would be my 2 structures. All right, and then in F, so F is going to be kind of the opposite of this. So this followed Markovnikov's rule. This was, regioselective in the sense that carbocation is forming on the more substituted position, which forms the alcohol on the more substituted position.
For the previous one?
I'm sorry, what was that?
I have a question for the previous one.
Yeah, sure. What's up?
Wouldn't that ethyl be dashed as well?
The ethyl be dashed ethyl. Yeah, I don't know why. Yeah, I don't know why I didn't do that. Thanks, guys. So yeah, definitely, and then this one would be wedge as well. Sorry, I don't know why that happened. All right, thank you. So for F, okay, so we're using this reagent called borane, BH3, and borane is selectively chosen. I think I gave you guys kind of a good explanation of why borane is used, and there's a sterically hindered side and a sterically unhindered side of borane. So what that basically means is I'm going to have my BH2 fragment aligned to the less substituted side, and then that singular hydrogen of borane, added to the more substituted side. So essentially the mechanistic arrows are this nucleophile pi bond grabbing that bromine, and then, this bond right here, this boron hydrogen bond forming back at that position. Okay? So the result is synaddition, okay, synaddition of the BH2 and the H fragments. Okay, so that would be something like, let's say, I know this is an achiral center, but I'm just doing this for, your guys' purposes. Those two would be coming on the same phase. Okay, and then you also have the wedge version as well, the wedge. So plus enantiomer. And then what step 2 does is it's just a source of hydroxide, and that's just going to replace this group BH2 over here. So again, we don't know the mechanism beyond this, but you can just imagine that we're replacing those BH2 groups with OHs, and it forms these anti-Markovnikov or less substituted alcohols. Okay, so we actually have no stereochemistry to consider here, and there are no rearrangements because we didn't go through a carbocation. So we're here. But we did generate a chiral center in the process. Do you see we took this, planar pi bond away, so that makes this, a chiral center now. So we would have to consider, the wedge version plus dash version. Okay, and that's it. So I know that's a kind of crazy piece of paper, but those are our 6 main reactions, and I tried to give you guys some quick mechanistic steps and facts to remember. Anybody have any questions? Sorry, I can't see the product for D. Where was D again? D should be here. Okay, so D should be here. I circle this one, that's D. Anybody else? All right, awesome. So that's basically most of chapter 6. So now we're going to move to the student workbook, and we're going to be on page, let's see, we're going to be on page 68. Okay, so if you guys are following along with me, here we are. We're on predict the product, letter JJ. And this is really one of the coolest reactions in all of Orgo that you guys will learn, and this is ozonolysis. And it's awesome because you don't have to know a mechanism for it. You just have to like recognize these reagents, and it's the same thing every time. So step one is ozone. Okay, so ozone is 3 oxygens, all linked together, and it's what's primarily in our atmosphere. And then we have this reagent called dimethyl sulfide. Okay, so dimethyl, so 2 methyls and a sulfur. Sometimes you'll see it abbreviated as DMS. And I come into contact a lot with this in my organic lab. We use DMS as an NMR tool. So you guys will learn a lot about NMR in Orgo 2. It's a way for us to identify like what molecules are in liquids, like what molecules organic based are in these structures. It's kind of cool. So anyway, you guys will see DMS coming up. But point is whenever you see a pi bond and you're doing ozonolysis, you want to literally draw a line right through it. So let me pick it one color. Okay, you will draw both fragments the exact same. Okay, so by this I mean this is fragment 1 down here, fragment 2 up here. So my fragment 1, I'm going to draw right here. So exact same thing, literally in the exact same structure. Okay, so it's fragment 1. And then fragment 2 is going to be okay, so notice I just cut both ends of the pi bond, and then all you do, boom, boom, put an oxygen. Done. That easy. Okay? Don't rotate, don't try to do any crazy things. Just cut at that position and draw 2 pi bonds. Draw 2 oxygens. Sorry about that. Okay? The next one, let's try this one, KK. So again, cut, don't do anything fancy. So all you want to do here is leave these, because we're not doing any chemistry with these carbonyls yet. That's Orgo 2. And then, okay, so that's where we cut, do the exact same thing, and just put an oxygen there. Okay, so you could write the equivalent structure. So I'm going to do this. This is what I would typically do on a test. So I would draw this structure first. Okay, and then I would do 1, 2, 3, 4, 5, 6, 7, 8. So that means I want to draw an 8 carbon chain. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So you draw an 8 carbon linear chain. On carbon 1, there was nothing. On carbon 2, there was a carbonyl. 3, nothing. 4, nothing. 5, nothing. 6, nothing. There was a carbonyl. 7, there was a carbonyl. And 8, there was an aldehyde. So this would be the linear format if I were to, elongate that. But you would also get full credit for just showing this one as well. Either one. I think I saw a question pop up. Let's see. Is 1 a ketone and an aldehyde in JJ question? Yes. Oh wait, no. They're both ketones. I think that's the question you're asking. These are both ketones here in JJ because we have carbons on both ends. I think that's your question. Okay, let me know if that clarified it. Okay, yeah. Great. All right, so that would be KK. And then in LL, same thing. So remember, draw a line through it. Draw your exact same fragments the way that they are, but then just add an oxygen. And then that was fragment 1, so let's draw fragment 2. So basically you're forming these carbonyl structures where these pi bonds used to be. Okay, and you could draw the hydrogen here if you want for the aldehyde. Okay, so you actually get 2 products here. Okay, MM, same thing. So I'm just going to cut through there, draw these. Okay, so I think these are pretty self-explanatory at this point. And finally, an N. So we're going to cut here. Okay, so let me number this ring. 1, 2, 3, 4, 5, 6, 7, 8, 9. So a 9 carbon ring. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so on position 2, that's where that carbon-carbon double bond was. So that would be where my new ketone is going to be. And also on carbon 8. That's it. Okay, any questions on ozonolysis? Very easy. Awesome. All right, so let's move on to syn-diol synthesis. Okay, so in syn-diol synthesis, this is, second to last one that we have. And we have, again, a partial mechanism to know. Okay, let's do this over here. So let me do OO on a separate sheet of paper. I'll show you guys what I mean. Okay, so what we're going to do is we have this pi bond. And we have this structure. So again, there really are very few things to memorize in orgo, and I just think this structure is definitely, this Lewis structure is worth knowing. This is osmium tetroxide. So this is also known as OSO4. Okay, so osmium is, a metal that we typically don't see, but then we have all these carbonyls that allow us to react with that osmium. Okay, so this is another concerted mechanism where, this pi bond is going to go here, this is going to go here, and this is going to go here, okay? So this nucleophilic pi bond is going to form a bond to this oxygen, okay? One of these pi bonds has to break because we exceed the octet for the oxygen, forming a lone pair on the osmium, and then that also exceeds the octet for osmium, so we have to kick one of these pi bonds out, okay? So the result is a structure that looks like this. And we also have, well, this would be a meso compound, so I actually don't have to draw it. So the other one, but it would be meso because it's a plane of symmetry. So we don't have to draw the other one. Okay. So this would be what we call the cyclic osmate intermediate. Cyclic osmate intermediate. So sometimes you might have that question, draw the cyclic osmate intermediate, draw the mercuric acetate intermediate for oxymercuration, draw the, hydroboration intermediate with borane. You have all these different intermediates within the mechanism that you could also be asked to draw. Okay, so that's the step one, okay, from osmium tetroxide reacting. But you can see that we have all these other reagents. We have water and, peroxide. So what do? Well, water is basically going to do hydrolysis. And you don't need to know this in terms of a mechanism, but hydrolysis means just to cut with water. So we're going to cut with water at that position, okay? So the result would be forming these hydroxides. Oops, I know I'm drawing these really fast, okay? And this was meso, so I don't have to draw the dash one either. Okay, so that would be what happened. What hydrogen peroxide does is, this leftover starting material with hydrogen peroxide is going to regenerate those carbonyls. So it's going to go back to that osmium tetroxide. So again, for your purposes, water and the hydrogen peroxide aren't really going to, be relevant for this reaction, but they are there. Don't forget to write those in if you ever have to type them in. They are important, but in terms of, just your main reagent here, osmium tetroxide is the biggest one to know. Okay, and it's forming these syn-diols. So it's stereospecific in the sense that we form two, of the same stereochemical configuration chiral centers. Okay, so that is this one. Okay. But we don't have to do that full concerted mechanism each time. It's really easy. So for PP, let's just look over here. We see that we have, this ethyl group stays the same because we're not doing any chemistry here, but we could have formed, wedge hydroxyl, and then we could also do dash hydroxyl. Okay, that's it. So these would be the geometric isomers there. Same thing for, QQ, RR, SS, keep going on. So, but one thing we all have in common here, and this is a segue, is that these are all Z alkenes. You notice how they're all Z alkenes? Okay, so keep that in the back of your head. Just remember, maybe write this under here, Z alkenes. Wink, wink. That's going to help you with some chapter 7 stuff. So we're not there yet, but keep in mind Z alkenes. Okay, so we're on the last reaction. Okay, catalytic reduction. This is the easiest, and and being completely honest, it's the simplest one, but it comes up every single time. Like in every chapter, it's going to come up in a synthesis. It's going to come up in Orgo 2. Like this is a very important one to keep in the back of your head because it's used a lot. Okay, so this is a way of adding hydrogens to unsaturated, organic molecules, and when you add this hydrogen, it makes it saturated. So I'm actually going to digress for a second and give you guys some connections here. So phospholipid, right? So back to bio, phospholipid. We can either have that, or we can have, okay. So we can either have all of our fatty acid tails being, in this trans arrangement. So this is the trans fatty acid. Okay, and it's trans because, each one of these carbons has the complete amount of hydrogens added to them. Okay, so this would be considered trans, this trans fatty acid, but it also is saturated, right? So it's saturated. Okay, and then this one is, this one might be trans, but this fatty acid is definitely, cis, because we see that we have, this, I didn't draw it that great, but it would be, you know, cis, that cis orientation right there, so cis, and it has a pi bond. So what does that pi bond do? Well, that pi bond actually removes, instead of there being two hydrogens there, there's only one at each carbon around that double bond. So it's actually considered unsaturated. So this term saturated just refers to how much hydrogens are added to these fatty acids. And you're unsaturated when you don't have all the possible hydrogens bonded to those carbons due to some sort of pi bond. So in all these structures, we have these unsaturated, you know, structures, and we're going to saturate or reduce, because saturate means to give, right? And reduction means to give. So we're going to give these electrons and protons to these unsaturated molecules and saturate them, or make them just all full carbon CH2 bonds, okay? And it requires some sort of inert catalyst. So this platinum, palladium, or nickel with them. Either one doesn't matter. Any of them, like I always just do H2 and platinum because it's the first one that's in my head, but nickel, platinum, or palladium is fine, okay? So, you know, this is syn addition where the hydrogens of H2 are added on the same phase. Okay, so we always assume excess. So that means that all of these deficiencies, all of these unsaturations will become reduced. So that means, if that's the structure, that means that's it. Okay, and we added hydrogens to, you know, this part, this part, this part, this part, this part, this part. So hydrogens were added all over there, and that's why we have that structure. Okay, for this guy, this one's a little different. So in order to show that you added it via syn addition, okay, you have to show that the hydrogens came on the same phase. Okay, so before, since these weren't chiral centers in the sense that, you know, we had two hydrogens there, it was fine. But here, you know, these are chiral centers, so we have to show that they came on the same phase. You have a question on that one? I know that sometimes trips people up, why we have to show this explicit hydrogens when we typically don't do it. Okay, but these are two of the same structures. I don't know if you can tell, because if I pancake flip this over, it'd be the exact same. The reason that is we have, you know, a plane of symmetry through this, so you could just write one of them and write me so. Okay, that's that. For VV, so H2 and platinum, so maybe this structure will help you. So the hydrogen gets added, H2, like that. That is what syn addition is. And it could also be added on the wedge as well, so it just depends. So if it is added on the dash, that forces this ethyl group up. Okay, so then that would result in, and then we also can't forget this other diastereomer. Okay, so those two structures, and that's that. Let's do WW. So again, we're going to add, let's say it's hydrogen on a dash, hydrogen on a dash. That would result in a structure that looks like wedge, wedge. And then we can also do the other one. Dash, dash, okay? And for this guy, I think you can kind of rationalize. It would basically be wedge, wedge, get rid of that pi bond, or dash, dash. And there's also another one here. So then this group, actually, let me draw this one. This one's probably important because it's a lot of stereochem. The UU, and UU is the dash product crossed out. Yes, it is, because you can see that there is a sigma plane right through here. Okay, so if I were to like literally go like, flip that over, they become dashes. It's the exact same structure. There's no reason to draw it twice. Okay. Let me draw XX out again. So got ahead of myself. Okay, so there's two pi bonds here. We're going to assume that there's excess reagents going to react with both of these pi bonds. So the first one I'm going to think about is maybe this, the substituent that's on the ring. So let's add, you know, dash dash. That forces this whole entire carbon chain substituent on the ring to be a wedge. So that would make sense for us to do this. Okay, so that's, you know, the first, you know, I guess, addition of hydrogen, and that's also going to lead us into, you know, maybe this dash version as well. Okay, and then, you know, for these hydrogens, those could have been added on the wedges or the dashes as well. So let's say, you know, I'm going to add, you know, wedged methyl here, wedged methyl here, but I could have also added it to the dash version. So maybe let me also show this. Okay, and then same thing over here. They could have been added on, you know, the back face, which forces these methyl groups to be wedges. Okay, and then I think, did I drop a carbon here? Something's off. Oops. Yeah, I put this over too far. Not that. Ignore this. Ignore that. Sorry. And you also have this guy. Okay. So you have these 4 major stereoisomers, okay? Kind of crazy. All right, so I think that's it for our alkene reactions. Does anyone have any questions so far? That covers everything. All right, so we're gonna move along just a little bit. And this is the next thing, that last part of chapter 6 on the cancer there on the 2 students with that one. There are only 2 stereoisomers. Let me see something. Okay, out of 1, 2, 3, 4, which ones are shown on the key? You can type it in the chat box.
I think they're shown on the key without the stereo chemistry of the like when it starts to branch.
Oh, these branching? She left it kind of the same.
Like off of the cyclohexane.
Got like this stuff. She's not showing this. Yeah. Okay.
Yeah,
So that must have just been an error then, if that's true, because these, you know, this pi bond definitely gets, you know. Oh, actually, you know what? Okay, guys. The reason why this is such a stupid mistake. The reason why is because this is not a chiral center. Do we all see that? I didn't notice that either. The left and the right side of the ring are technically the same, you know, substitution. So that's why. Okay, so that makes sense. So let me fix this one for you guys. I think hopefully that makes sense for I mean, I made the mistake too. So basically, yes, you're right to think this. If this was, you know, if this was not, you know, symmetrical on the left and the right side of the ring, we would have to do this. So it's actually good that we did it. But basically, I guess what we should have done was, you know, showing that it could have been wedge from that position, or it could be dash on this position. Awesome. Good catch, everybody. So I think that's what it is, 1 and 4, without these groups. Okay. All right. Great. Glad we figured that out. Okay. So then we're moving on to this last stuff over here. So this is really the last kind of topic in chapter 6. I actually think it has to do with chapter 5. I don't even know where it is, but whatever. Point is, it's here. So we're going to rank these alkenes in an order of increasing stability. So this is really easy, honestly. No thinking. A more substituted alkene means it's more stable. No thinking. So meaning if there are 4 carbon groups that are attached to it, it's more stable than 3 carbon groups, which is more stable than 2, which is more stable than 1. That's it. So if we look at these, you know, in letter A, we have, you know, a tetrasubstituted alkene, meaning we have 1 group, 2 groups, 3 groups, 4. Here we have a tri-substituted, 1, 2, 3. Here we have a di-substituted, 1, 2. And here we have a mono-substituted, 1. So that's really easy. So then we just rank these as 4, 3, 2, 1. No thinking. Oh, it's already in order. Okay, so then for now we have to deal with these. So all of these are, you know, looks like di-substituted, 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 oh, and tri-substituted. Okay, so tri is definitely my best one. Okay, and then how do I delineate between these various types of di-substituted alkenes? Okay, so we have trans, we have cis, and we have something called geminal. Okay, so those are your 3 words you should know. You already know trans and cis. Trans, cis, and when they're both on the same carbon of the pi bond, it's called geminal. Okay, and it's an intermediate energy structure between the trans and the cis. Okay, so, you know, why did we say, you know, the anti-conformer is the best Newman projection? And it's because it's totally 180 degrees apart. We have the minimal amount of steric interaction. So trans would definitely be my next most stable. Okay, then, you know, between cis and geminal, remember around this, you know, pi bond, it's 120 degrees, all of these substituents. So, you know, this group and this group are 120 degrees apart from another eclipsed. Okay, so they're only 120 degrees apart. So that's pretty decent. And then we have cis. So if you can tell, look how close these CH3 groups get to one another in the cis conformer. They're not 120 degrees apart. They are really, really close. So this would be something like an eclipse conformer. So that would be 1, the worst one. Okay. So in terms of your di-substituted ones, the order goes trans, geminal, cis. Okay. Anyone have any questions on that? Really easy. Just keep that in the back of your head. All right. So 13 is something you could see on your test for sure. Okay, so definitely be familiar with this type of web structure. Okay, so we can give you one starting material and kind of just subject it to a whole bunch of different reagents. So this is kind of going to be our last thing that we talk about today. How much time? I know we have a lot of time. This is one of the last things we'll talk about today because it kind of solidifies all of those reactions again. So let's just talk about those. So let's start with A. So it looks like we have bromine and then we have some sort of alcohol. So we haven't seen bromine and alcohol, we've seen bromine and water. Okay, don't freak out, it's the exact same thing. Okay, so a big hint for you guys on your test is if you see something you don't know, you definitely have the knowledge from some reaction that you know to answer it, 100%. There's not gonna be anything on it that is way out of your reach, okay? So yeah, like I don't recognize this is water, but I recognize that it's methanol, so you know, it probably reacts the same as water, okay? And that's fine, that's a very fair assumption to make. All right, so let's kind of do these to the side. Okay, so I'm gonna draw, you know, this guy over here. Okay, so I'm gonna draw okay, so we have the skeleton framework, and you know that bromine is probably gonna do some sort of like bridged intermediate, okay, nothing new. Okay, and then remember that methanol is gonna attack the more substituted side for reasons that we discussed earlier. So we're thinking methanol, and I'm doing these quick, I'm not really drawing the full mechanism, but I'm definitely assuming it's gonna attack at that side, and remember, it's gonna do anti-addition, adding on the opposite base. So this is like what should be going on in your head, like as you are answering these questions, like you should be thinking these things. Okay, so then I can pretty much assume what my products are gonna look like in 2 seconds, and I can say, okay, if this bridge was a wedge, then that methoxy group has to come in on a dash. Okay, which forces that methyl group on a wedge, and then that bromine can stay as a wedge. Done. Okay, then also there's one more. Don't forget, if this bromine bridge was on a dash, then that methoxy group had to have come in on a wedge, which forced the methyl on a dash, and then since the bridge was already a dash, we can leave it as such. Okay, so those would be the structures for A. Okay, any questions? Great, and that's the structure for A. Okay, so for B, it looks like we're doing hydroboration reactions. Okay, so that means we're gonna add an alcohol to the less substituted side. Okay, no thinking for me. What side is the less substituted side? Okay, here, definitely not, so clearly here. So all I wanna do for B, so I guess I can just draw it on my paper. For B is draw this. Hold on 1 second. I actually think I just made a mistake. Yes, 1 second. BH2 goes here. 1 second. BH2 here. There. Yeah, okay. So remember that it's syn addition like this, okay? So it's syn addition like that. And then what happens is that this source of hydroxide is going to replace this position. But do you notice how this, you know, hydride is on a dash? So if it's on a dash, that means that that methyl group needs to be on a wedge. Okay, so that's how I got the wedged methyl group, okay? And then that hydroxide is just gonna come in and replace this position of the BH2 group. So that could just be, you know, wedge hydroxyl. And then I think there's one more product. It's here, and it is, oh, I'm sorry, this should have been dashed. Dash, ugh, I know this is messy. Okay, so wedge, wedge, dash, dash. Okay, you guys get those? Dash, dash, wedge, wedge. Okay. All right, so C we just kind of talked about, H2 and platinum. So this is, again, syn addition of the hydrogen. So if they're added, you know, basically both maybe, you know, dashes, then that would result in that structure. And then it also results in that structure because it was added on wedges. Just those two. D, ozonolysis, remember just cut. Okay, so those are my two products there. Pretty easy. Okay, so E is ozonolysis. I'm sorry, E is osmium tetroxide, so that's a syndiol synthesis. Okay, so then what we're going to do here is take this benzene ring, and we're going to form a syndiol on it. So essentially, I want to do a wedge hydroxyl, a dash there, and I want to also add a wedged hydroxyl here. And then I can also draw the opposite of both of them being on dashes. Okay, so 1, 2, 3, 1, 2, 3, yeah. All right. So notice how they're syn. Oops. So both hydroxides have the same stereochemistry. Okay. All right, and F is our last one, really easy. So we see that we have, this is hydrohalogenation, the first reaction we ever learned. So we're forming a carbocation on the tertiary benzylic position. Chloride's gonna come in and attack. So I'm just gonna go right to those products at this point. And I see that I have this, that, and you also have that, all right? And that's how I would do these, okay? So again, like if you guys know these reactions, there's only 10 so far. They're pretty easy, like, so you can do these pretty quickly. All right, and we can now, I wanna go back to this one question because I just like this question a lot. I think it's really important. So we talked about A, C, and D last class in terms of how to discover if it's stereospecific, regioselective of both, neither. And we didn't talk about B because we didn't know what B was. So what B is this, syndiol synthesis. Okay, syndiol. Diol just means two alcohols. So if it's syn in the name, we're saying syndiol, that means it must be stereospecific. But is it regioselective? I don't really have one region that I'm attacking more so than the other, so I would definitely just go with stereospecific. Okay? So I think we all understood why A and C were both. They were both in the sense that we had one specific region. Remember, water was attacking on that more substituted side. Borane is aligning specifically at the less substituted side. Those are regioselectivity arguments. But in terms of stereospecificity, remember, if you're going through a carbocation, where you're going through like these syn or anti-additions, those are stereoselective processes. So those would be both. Okay? Remember, it was syn addition of the BH2 and the H fragments here, and it was, this concerted mechanism of that bridge, okay, which caused that anti-addition, remember? So these are all these things you should keep in mind. Okay, so let me just add like E real quick. Let me just add one more. And let me say, maybe something like this. And let me add H2 nickel. And let me add that. What is that one? Is this stereospecific, regioselective, or neither? Okay, well, if you said, stereospecific, you're totally right, because this is syn addition of, remember, those two hydrogens. So either wedge, wedge, dash, dash. So that's how to rationalize those. All right, and that kind of takes us through chapter 6. Definitely practice with these mechanisms. So, you obviously see the products already, but try and, work out each mechanistic step and see if you guys are right. So, we don't necessarily know the full mechanisms for, oxymercuration, hydrohalogenation, or, syndiol synthesis, but you do need to know how to get to these intermediate structures. So you should know these first steps in the mechanism for that, even though we don't know the full one. Okay. I'm going to stop there for today, and I'm just going to pick up alkyne stuff next week. I think you guys have a test next week, right? So can someone confirm that for me? You guys have a test? Yeah, okay. So we'll be chilling for chapter 7 because chapter 7 is really just an extension of chapter 6. So what my plan is for you guys is to finish pretty much all of the chapter 7 reactions I'm going to do in one sitting on Monday. So definitely be here for that. And then Wednesday, I want to do a complete synthesis day. Okay, so what synthesis is, if you haven't seen this, it's page 84. This is the most tedious part of your exam. Okay, 84 and 85. So we're going to talk about this a lot when we meet on Wednesday, and we're just going to spend all of Wednesday dedicated to that, and we'll see how we're feeling on Thursday or Friday. Okay, so that's it for now, and I hope that helped you guys, and keep working. You guys got it.